Determinant expansion using cofactors. Welcome, everyone. Before we dive into today's new topic, let's take a moment to reflect on what we have already covered. In our previous lessons, we spent some time learning the mechanics of how to calculate the minor, denoted as m sub ij, and the cofactor, denoted as a sub ij, for any specific element within a determinant. You should now feel comfortable finding those values. Now, it is time to take those building blocks and put them to work. Today, we are going to move beyond just finding individual pieces and learn how to apply these concepts to find the actual, total value of an entire determinant. This systematic process of breaking down a large determinant into smaller parts is what we call determinant expansion. By the end of this session, you'll see how expansion allows us to solve much more complex matrices with ease. The concept of expansion. Think of expanding a determinant as a way of breaking down a complex problem into smaller, more manageable pieces. When we talk about a higher-order determinant, like a 3x3 matrix, it can look a bit intimidating to solve all at once. Expansion is the process of reducing that larger determinant into a sum of smaller, lower-order determinants, for instance, turning a 3x3 into several 2x2 determinants. These smaller versions are much easier and quicker to calculate. The most important principle to remember here is the beauty of its consistency. The value of the determinant, which we represent by the Greek letter delta, remains exactly the same regardless of which row or column you decide to use for your expansion. This gives you a lot of flexibility in your work. You aren't locked into any specific path. You can choose to expand along any single row or any single column of your choice. As we will see in the next slide, there is a specific mathematical formula that governs this, and in the following steps, I'll show you a strategy to pick the most efficient path. Now that we've refreshed our memory on what minors and cofactors are, let's talk about the core concept of expansion. The mathematical formula. If we decide to expand a determinant, which we denote by the Greek letter delta, along the ith row, the value of that determinant is found by taking the sum of the products of each element in that specific row and its corresponding cofactor. Mathematically, we express this as delta equals a sub I1 times a sub I1, plus a sub I2 times a sub I2, and so on, continuing through to a sub IN times a sub IN. The beauty of this method is that the same logic applies vertically. Similarly, if we choose to expand along the JTH column, the value is the sum of the products of the elements of that column and their respective cofactors. This is written as delta equals a sub 1j times a sub 1j, plus a sub 2j times a sub 2j, continuing down to a sub nj times a sub nj. Now that we understand the concept of reducing a larger determinant into smaller ones, let's look at the formal mathematical formulas used to perform this expansion. In the next slide, I will show you a systematic, step-by-step procedure so you can apply these formulas accurately every single time. Step-by-step procedure for expansion. Now that we understand the mathematical formula for expansion, let's break this down into a practical, step-by-step procedure so you can approach any problem with confidence. To calculate the value of a determinant, you should follow these 4 systematic steps. Step 1 is selection. You have the freedom to choose any single row or any single column to work with. However, here is a professional tip to save you time and effort. Always look for the row or column that contains the maximum number of zeros. Since anything multiplied by 0 is 0, this will significantly reduce the amount of work you have to do. Step 2 is identification. Once you have made your choice, clearly identify the elements within that specific row or column. For instance, if you decide to work with the first row of a 3x3 matrix, your elements would be a sub 1-1, a sub 1-2, and a sub 1-3. Step 3 is cofactor calculation. This is where we apply what we learned in our previous lessons. You need to find the cofactor for every element you identified in the previous step. Just a quick reminder of the formula. The cofactor, a sub ij, is equal to -1 raised to the power of I plus j, multiplied by the minor, m sub ij. Finally, step 4 is multiplication and summation. Take each element from your chosen row or column and multiply it by its corresponding cofactor. Once you have all those individual products, simply add them all together. The final scalar value you get from this sum is the actual value of the determinant. In the next slide, we are going to put this exact 4-step process into practice with a concrete numerical example. Illustrative example. Take a look at this problem on the screen. We are asked to find the value of the determinant, which we will call delta. The determinant is a 3x3 matrix consisting of the elements 2, -1, 3 in the first row, 1, 0, 4 in the second row, and -2, 1, 5 in the third row. To solve this, we need to apply the expansion method we just discussed. As I mentioned in the previous slide, we have the freedom to choose any row or column. While we could pick the second row because it contains a 0, which would make our work easier, for the sake of demonstrating the full process, let's expand along the first row. Let's move through this systematically using our 4-step procedure. Step 1. Identify the elements of our chosen row. Looking at the first row, our elements are a sub 1, 1 equals 2, a sub 1, 2 equals -1, and a sub 1, 3 equals 3. Step 2. This is the most critical part, calculating the cofactors for each of these elements. Remember to include that alternating sign from our formula. First, for our element 2, which is at position 1, 1. The cofactor, a sub 1, 1, is calculated by taking -1 to the power of 1 plus 1, which is just +1, and multiplying it by the minor determinant of the remaining elements. That minor is the determinant of the 2x2 matrix with 0, 4 in the top row and 1, 5 in the bottom row. Calculating this, we get 0 times 5 minus 4 times 1, which equals -4. So our first cofactor is -4. Next, let's find the cofactor for our element -1, which is at position 1, 2. Here, the sign is -1 to the power of 1 plus 2, which gives us a negative sign. We then look at the minor determinant using the elements 1, 4 in the top row and -2, 5 in the bottom row. This gives us 1 times 5 minus 4 times -2. That simplifies to 5 plus 8, which is 13. Since we have that negative sign from the position, our cofactor, a sub 1, 2, is -13. Finally, for our third element, 3, at position 1, 3, the sign is -1 to the power of 1 plus 3, which is +1. The minor determinant uses the elements 1, 0 in the top row and -2, 1 in the bottom row. Calculating this, we get 1 times 1 minus 0 times -2, which is simply 1. So our third cofactor, a sub 1, 3, is 1. Step 3. Now, we apply the expansion formula by multiplying each element by its corresponding cofactor and summing them up. Our equation is delta equals a sub 1, 1 times a sub 1, 1, plus a sub 1, 2 times a sub 1, 2, plus a sub 1, 3 times a sub 1, 3. Plugging in our values, we get 2 times -4, plus -1 times -13, plus 3 times 1. Let's do the arithmetic. 2 times -4 is -8, -1 times -13 becomes +13, and 3 times 1 is 3. Adding these together, -8 plus 13 gives us 5, and 5 plus 3 results in 8. So, our final answer is that the value of the determinant is 8. Now that we have understood the theory and the step-by-step procedure, let's put everything into practice with an illustrative example. As we move to the next slide, I want you to think about how this systematic calculation relates to real-world complexity, much like an audit of a large project. Real-world analogy. Now, I know that all those calculations with minors and cofactors can feel a bit abstract and purely mechanical. So, to help you grasp the intuition behind why we use this expansion method, let's step away from the numbers for a moment and look at a real-world analogy. Imagine you are a project manager responsible for calculating the total cost of a large-scale project. This project is divided into 3 distinct phases, which we can think of as our rows. Within each of these phases, there are various specific tasks, representing our columns. Now, to find the total cost, you can't just simply add up every single number you see in your spreadsheet. Instead, you have to look at each task and weight it by its specific impact factor. This impact factor is very much like the cofactor we just calculated in the previous steps. It represents how much that specific task contributes to the overall outcome of its phase. The entire process of determinant expansion is essentially like performing a systematic audit. Instead of being overwhelmed by the whole matrix at a time, you analyze the project one phase at a time. You calculate the impact of each task relative to the rest of the project, and then, by summing all these weighted products together, you arrive at your final total. This way, you can see that expansion isn't just a random procedure. It's a structured way to break down a complex, high-order problem into manageable, smaller pieces. However, as we move to the next slide, I want to warn you about some common pitfalls where this audit can go wrong if you aren't careful with your signs and selections. Common mistakes to avoid. First, let's talk about sign errors. This is, by far, the most frequent mistake I see. When you are calculating your values, many students accidentally use the minor instead of the cofactor. Remember, the cofactor is not just the determinant of the remaining submatrix. You must include that alternating sign term, which is -1 raised to the power of I plus j. A simple way to keep track is to remember that the sign flips. It becomes negative whenever the sum of the row index and the column index is an odd number. Second, watch out for incorrect minor selection. When you are finding the minor of an element, denoted as m sub I, j, you must delete the entire row I and the entire column j. I have seen many students mistakenly only cross out the single element itself, which will lead to an incorrect submatrix. You must remove the full horizontal and vertical lines intersecting at that element. Finally, be vigilant regarding arithmetic slips. Determinant expansion involves a lot of multiplication and addition, and it is very easy to lose track of a negative sign. For instance, if you are multiplying a -1 by a -13, ensure you correctly arrive at +13. One small slip here will cascade through your entire calculation and give you the wrong final answer. Stay focused on your signs, and you will find much more success. Now, before we wrap up our lesson and move on to our final summary, I want to pause and discuss some common pitfalls. Even if you understand the concept of expansion, it is very easy to lose marks due to small, avoidable errors. Please pay close attention to these 3 points. Key takeaways. First, remember the concept of flexibility. As we saw in our step-by-step procedure and our worked example, you aren't locked into using just the first row. You have the freedom to expand along any single row or any single column you like, and the beauty of this method is that the final result will always be the same, no matter which path you choose. Second, keep the fundamental formula in mind. The value of the determinant, which we denote as delta, is simply the summation of each element multiplied by its corresponding cofactor. It is essentially a weighted sum. Third, I want to emphasize the importance of efficiency. While you can pick any row or column, always look for the one that contains the most zeros. As we discussed in our tips, multiplying any cofactor by 0 results in 0, which significantly reduces the amount of arithmetic you have to perform and helps you avoid those common arithmetic slips we mentioned earlier. Finally, understand the core purpose of this technique, which is order reduction. The entire goal of expansion is to take a complex, higher-order determinant, like a 3x3, and break it down into a sum of smaller, lower-order determinants, such as 2x2 matrices, which are much easier to manage. To wrap up our lesson today, let's review the key takeaways to ensure you have a solid grasp of determinant expansion. If you keep these 4 points in mind, you'll be well on your way to mastering determinants. Great job today!